We will now do questions of X-ray, but before we do the examination question, we will revise what are the important things that we need to know. For theory, we need to know how to explain how X-rays are produced by electron bombardment of metal target. You need to link the energy of the X-ray photons to the energy the electron gain from the accelerating potential difference. Then you must understand the use of X-rays in imaging internal body structures, including the use of contrast like barium mutes and iodine dye in the bloodstream. The formula and calculation that you need to know in this chapter will be, number 3, this is a formula you need to know. I equals to I0 e to the power of minus mu x for the attenuation of X-rays in matter. Then number 4, know that the attenuation coefficient mu depends on the density of the media. The higher the density like bone, the higher the mu. And then number 5, link the attenuation coefficient to the half value thickness XH of a material. This formula is important because it allows you to calculate your mu knowing your XH, and you can find XH knowing your mu. In this past year question from October, November 2009, variant 42, question number 10. Part A, a typical spectrum of X-ray radiation produced by electron bombardment of a metal target is illustrated in figure 10.1. This is the Bremsstrahlung radiation. This is the minimum frequency, a minimum wavelength, and then this is the spikes. Explain why a continuous spectrum of wavelength is produced, referring to the breaking radiation here. Electromagnetic radiation is produced whenever a charged particle is accelerated. The wavelength of the radiation depends on the magnitude of the acceleration. The electrons hitting the metal have a continuous distribution of acceleration. Then part 2, the spectrum has a sharp cut-off at short wavelength, referring to this point here. So this is part 2. Part 2 is referring to this part. All the energy of the electron is lost to form a single photon of X-ray. So the theory is that energy equals to HF, energy equals to HC over wavelength. So your wavelength, which is this wavelength here, equals to HC over E. HC is Planck constant times the speed of light, which is constant. Therefore, your wavelength is inversely proportional to the energy, which depends on your V times E. V is the potential difference between the anode and the cathode. So lambda is minimum when E is maximum. E is maximum when the electron loses all its energy in one collision. In part B, the variation with photon energy E of the linear absorption coefficient of X-ray in soft tissue is illustrated here. This is a mu, and this is the energy of the X-rays. Explain what is meant by linear absorption coefficient. Since this question got 3 marks, you can use the equation and explain all the symbols used in the equation. I equals to I naught e to the power of minus mu x, where I naught is the initial intensity before absorption. I is the intensity after the X-ray photon travels the distance x. X is the distance traveled by the X-ray, and mu is a linear absorption coefficient. And then you must understand that this formula only applies to a parallel beam of X-ray in matter. Then in part 2, for one particular application of X-ray imaging, electrons in the X-ray tube are accelerated to a potential difference of 50 kilovolt. Use figure 10.2 to explain why it is advantageous to filter out low energy photons from the X-ray beam. Low energy photons are less penetrating as they are easily absorbed. Low energy photons do not contribute to form X-ray image. However, the energy can still pose a danger to living cells. That's why removing them is an advantage to protect the patient from the X-ray radiation.